So let us start with the introductory session of manifolds. Uh, so let me begin with the discussion that uh, we have already studied a bit of concepts on differential geometry. Okay. So we have discussed uh, some concepts of differential geometry, which is a most important branches in modern mathematics, in which one will have a great deal of study of geometrical problems. Okay, which will be viewed through the tools from will be viewed through the tools from calculus, right? Calculus, we will use linear algebra and also commutative algebra. Okay, and the basic objects in differential geometry are, the basic objects are smooth curves. Smooth curves. Smooth curve means where at each point you can get the notion of tangents and surfaces. So these are basic objects in the Euclidean space Rn, right? Now these notions will be encompassed through an abstraction in modern times, which will be named as smooth manifolds, right? So in modern mathematics, these concepts are encompassed through an abstraction, okay, through an abstraction which will be termed as smooth manifolds. So intuitively speaking, where you can talk of calculus in general setting, in some general objects, okay. Now, these notions in general has two motivations in particular. So, for the first one, we should be uh, we should recall that the usual Euclidean space is equipped with Cartesian coordinates. So, Euclidean space Rn, it is equipped with, as we all know that, it is equipped with Cartesian coordinates, right? Cartesian coordinates. So you can denote this by suppose T1, T2, Tn, right? And using this coordinate system, we have studied and built up the notion of calculus in n-dimensional Euclidean space, that is Rn, right? Now, sometimes we are tending to uh, change the coordinate system for our convenience to deal with some problems which are needed in times and very much useful to deal with those problems. Although with this kind of change in coordinates, you need to have an equivalent kind of notion of calculus which will be inherited from the notion of calculus that has been executed in the old coordinate system. That means which has been dealt with the old coordinate system will be transferred to the new coordinate system, right? Now, a natural question will arise that does calculus have any coordinate invariant concept? That is, if you change the coordinate system, the notion of calculus remains same. So, does it happen? That means, does there exist anything in calculus which is, or you can say that, does there exist anything in calculus which is invariant under the change of coordinates, right? And along this line, one may say that differential geometry in what remains of calculus after removing all the dependencies on the arbitrary choice of a coordinate system. Okay. So differential geometry is a more general kind of concept where you can talk of calculus by removing all dependencies with the coordinate systems. On the other hand, we would like to introduce smooth manifolds as we would intend to define a calculus on more general spaces that I am saying that I was saying in the first uh, statement, that basically we are intending to introduce manifolds, smooth manifolds, to define calculus in more general spaces. And in this context, smooth manifolds are spaces that are uh, that looks like uh, some Euclidean space Rn locally. Okay. So locally, that means you are suppose you have a topological space. Then around a point you can have an open neighborhood which is homeomorphic to some open set in Rn, or it is homeomorphic to Rn, or it is homeomorphic to some open disk, and on which we can execute the calculus. Okay. So just we are transferring the notion of calculus from Rn to a general kind of space. Now, besides Euclidean spaces, there are other familiar examples of smooth plane curves such as circles, parabolas, and also some smooth surfaces. Suppose you are in R3, so you will have some smooth surfaces like spheres, tori, paraboloids, ellipsoids, hyperboloids. And one may come across some higher dimensional examples of graphs of smooth maps. Suppose you have a smooth function, then its graph will represent a higher dimensional manifold. Okay. Okay. Smooth maps between two Euclidean spaces. Okay. So let me define first a topological manifold. Okay. So topological manifold. Okay. As a topological space with some certain properties that encode what we mean, what one can say that it locally looks like Rn. Okay. Locally means so around every point you will have an open neighborhood which is homeomorphic to uh, an open subset of Rn. But you need to impose more structure on manifolds to get important applications to geometry that would involve calculus. For example, whenever you need to study volume, curvature of spaces. So for that reason, you need to have some notion of derivatives, right, on general spaces. So to begin with, let us formally define topological manifolds. Whose precise definition is that a topological space, suppose we denote it by M, is defined to be an m-dimensional topological manifold if firstly M should be Hausdorff, is a Hausdorff space. What does it mean by Hausdorff space? What do you mean by a Hausdorff space? So for any pair of distinct points x, y belongs to M, there exist two disjoint neighborhoods around nx, x and y. Okay. So for any pair of distinct points, you can construct two neighborhoods which are disjoint. Okay. So one neighborhood containing x and another one contains y. Now, yeah. So number two, for every point P belongs to M. Okay. There exists a neighborhood UP of P in M which is homeomorphic to an open subset V of Rm. Okay, so for each point P, you will have a neighborhood UP containing P in M, which is homeomorphic to an open subset V of Rm. That is, there exists a neighborhood UP of P in M and an open subset V of Rm and a map phi P colon UP to V, which is a homeomorphism. Okay. Okay. And number 3. So although this condition seems to be unnatural here, but it will be clear from our later discussion that it is needed for the development of the theory of manifolds. So number 3 is M is second countable. That is, M has a countable base for the open sets. Okay. For the open sets of the topology defined on M of. Okay. So this is the definition of a topological m-dimensional topological manifold. Okay. So this is the basic definition of a manifold. So from axiom 2, that means this. So from axiom 2, you will see that. So from axiom 2, so you will see that, so for each point P, one can find an open set U of M containing P and an open subset V of Rm which are homeomorphic, right? Yeah. Okay. That means there exists a homeomorphism in between these two sets. That means an open subset U of M containing P and an open subset V of Rm, right? So there exists an open subset U of M containing P and an open subset V of Rm such that you can construct a homeomorphism in between these two sets. Homeomorphism phi from U to V. That means U and V are homeomorphic. What does it mean? That means you are transferring a a particular part of Rm onto the topological space M around the point P, right? Okay. So you are transferring a part, an open set, an open subset V of Rm to the space M around the point P. Okay. So locally M looks like an Euclidean space. Okay. Right. Yeah. And observe that this axiom is equivalent to saying that each point P has an open neighborhood U containing P that is homeomorphic to an open ball in Rm or to the open disk Dm in Rm or to Rm itself. Okay. So that means if you draw the picture, you will see that, okay, this is your M. Yeah. And suppose this is your P and this is your U. Okay. So around this P you will have an open set U, and you can set up, you can find out an open ball in Rm. This is your Rm. It's a schematic picture of Rm. So this is your V, okay, and this is your phi P. So you can construct a map phi from U to V. Okay. So you are transferring this V to U. Right? So that is why it is called, it is locally Euclidean. So that is why it is called locally Euclidean. Right? Locally Euclidean. Okay. That means for each point P, you can have an open neighborhood for each point P belongs to M that exists an open neighborhood U containing P that will be homeomorphic to an open ball in Rm or to the open disk, okay, Dm. Topologically they are same, Dm of Rm, open unit disk of Rn, okay. Or to open unit disk, sorry, yes, or to Rm itself, okay. So for that reason M will be called locally Euclidean of dimension M, okay. Okay, and the pair the pair uh, uh, phi comma u is called a coordinate chart. Okay, where coordinate chart, where u is an open subset of M, where coordinate chart, where u is an open subset of M and phi from u to v. What is v? V will be phi u, right? Is a homeomorphism. Is a homeomorphism from u onto an open subset v equals to phi u of the space Rm, right? Now note that in a topological manifold, every point P must be contained in some coordinate chart phi u, right? Because by axiom 2, because every point will have an open neighborhood u and an open subset v, which are homeomorphic. That means you are having some homeomorphism in between u onto v. Okay, so that is why you will have a coordinate chart phi u for the point P. So every point P will be contained in some coordinate chart phi u. So note that in a topological manifold, every point of M must be contained in some coordinate chart. Okay. Okay, coordinate I must say it is a coordinate neighborhood u for a coordinate chart phi u. Okay, right? Okay, where for every coordinate chart phi u, we call the set u as a coordinate neighborhood. Yes, coordinate neighborhood. Yes, coordinate neighborhood. And the map phi will be called a coordinate map. Okay, a coordinate map. Okay, also for a coordinate chart, for a coordinate chart, phi u, the component functions, the component functions are called local coordinates. Local coordinates on U. Okay, local coordinates on U. Okay, now if you find out, now if if we can have a collection of charts, a collection Carlier of charts of coordinate charts such that the UIs will cover M. Okay, then this collection will be called, is defined to be an atlas of atlas for M. Okay, okay, so that means in terms of this uh, this uh, concept of atlas, you can say that a topological manifold must have an atlas, right? So if you can have a collection A of coordinate charts with M equal to union U, then this collection will be defined to be an atlas for F. Okay. Okay. Now it should be noted that some a natural question will arise that suppose this is your M and this is your P. Okay. Now around P you may have two coordinate charts. Suppose this is Uy and this is Uj. Okay. You may have two coordinate chart. That means from Uy you will have a homeomorphism phi I, right? Suppose this is your phi p. 1 minute. Okay. So if you have two coordinate charts around a point P, Suppose this is your Uy and this is Vi, and then from Uj to another one, this is your so this is your phi jp, this is phi ip, yes, and this is your vj, and this map is phi j, right? Okay, these are Rm, this is your Rm. Okay, so let us consider two charts, two coordinate charts, phi I ui and phi j uj of the point P belongs to M. Then what will happen? Then you will have a transition map. This map will be called transition map from this space. What is that? So this is your phi I of ui intersection vj, uj. Okay, this part. This is your ui intersection uj. Okay. Then under this phi I, this part will be mapped to this one, right? So this is your phi I of ui intersection uj. See, in a similar way, this common part will be mapped to this part, and this part is phi j of ui intersection uj. Okay. So between these two parts, the shaded regions, you can set up a map from this to this in this manner. That is, phi ij is this is your phi I compose phi j inverse. Sorry, phi j compose phi I inverse. Yes, phi j compose phi I inverse. Okay. So firstly, phi I inverse will take this part phi I of ui intersection vj uj to this common part, and then under this map phi j it will map to this one. Okay. So this map will be called the transition map. Okay. And it should be noted that these transitions, so note that the transitions.
Hello, sir.
Bolo.
Hello.
Hello. Hello.
হ্যালো। হ্যাঁ স্যার, আমি বলছি স্যার এই ট্রানজিশন যে ম্যাপটা বললেন ওটা কি স্যার হোমিওমরফিজম হবে?
হ্যাঁ, সেটাই তো বলছি, সেটাই বলতে চাইছি, সেটাই
আচ্ছা
বলতে
স্যার,
চাইছি।
ঠিক আছে।
হ্যাঁ, হ্যাঁ, এই ট্রানজিশন
হ্যাঁ
ম্যাপটা
স্যার।
ইম্পর্টেন্ট একটা রোল প্লে করবে। So these transitions between different choices of, yes, choices of coordinates are called transition map maps, that is, which is phi ij defined as phi j compose phi I inverse from the set phi I of ui intersection uj to phi j of ui intersection uj, which are homeomorphism. Which are homeomorphisms. Okay, and these transitions map will give you an indication to define more general, more structure on the topological manifold M. It will give you more structure whenever we are uh, imposing some conditions on phi ij, right? Because these two sets are in Rm. So we are in Rm. So these maps are uh, the from a open subset of M to an open subset of Rm, right? So these are in Rm, right? These are all subsets of Rm. This is an open subset Rm. This is also an open subset of Rn. So in between two open subsets, these maps are defined. Okay. Okay. Now let us explore some basic examples of topological manifolds. Observe that the basic example of a topological M manifold is obviously Rm, right? The example, so the basic example will be Rm itself, right? As because it is housed of second countable and axiom 2 will be satisfied easily, right? Okay. Now, any null set phi is vacuously a topological manifold, which is called the null manifold or empty manifold. Okay. Now, any subset which is open, which is an open subset of a topological N manifold, will be a topological N manifold. So, any subset, any open subset of a topological N manifold will be a topological N manifold. So this can be uh, so this will be left as an exercise. Okay. Any null set is a topological manifold, and out of these basic examples, the first known or familiar example will be the unit circle. So let M is S1. S1 is the unit circle, right? X square, sorry. X square plus y square equal to 1. Now, obviously, in the basic topology course, we have already seen that this S1 is Hausdorff and second countable. So M is Hausdorff and second countable. Why it is second countable? Why it is second countable? Hello? Hello? Why it is?
স্যার রেশনাল গুলো নিতে হবে
Hmm?
এক্স কমা ওয়াই আর স্কোয়ার, ওখানে যদি ওই এক্স আর এক্স স্কোয়ার ওয়াই স্কোয়ার ইকুয়াল টু 1, যেখানে এক্স আর ওয়াইটা রেশনালে আছে, তাহলেই তো কাউন্টেবল হয়ে যাবে একটা।
হ্যাঁ, একদম। Okay. So this is house job and second countable. So now you can define an atlas. Suppose uh, we consider stereographic projection. Okay. Then you can find out charts, the coordinate neighborhoods. So which are u1. u1 is s1 minus 0 1, and u2 is s1 minus 0 minus 1. Okay. So firstly, so okay. Yeah. So in this way, okay. So what is u1? u1 is s1 minus 0 1. That is, it is punctured at the north pole. 0 1. Okay. And this is 0, and this is the south pole, 0 minus 1. Okay. And what are the associated maps, coordinate maps? The associated coordinate maps are phi 1, from u1 to r, defined by phi 1 of xy goes to 2x 1 minus y, and phi 2 of u2 minus u2 to r by phi 2 xy equal to 2 x 1 plus y. Okay. So these two maps are uh, continuous having continuous inverse. Okay, using the stereographic projection. Okay, fine. Also, so the atlas is, so the atlas of S1 is, so phi 1 u1, phi 2 u2. Okay, so therefore S1 is a topological, which topological manifold? U2 it is R, it is topological 1 manifold. Having an atlas consisting of two charts, coordinate charts. Okay. Also, you can define another atlas by defining just like that, another atlas. So suppose the coordinate neighborhoods can be defined as, so this is belongs to S1 such that y greater than 0, uh, u2, so this is xy belongs to S1 such that y less than 0, and similarly xy belongs to S1 such that x less than 0, and u4 is xy belongs to S1 such that x greater than 0. Okay, so that means, so if you draw the circle, then what does it mean? So what is u1? What is u1?
ইভেনটা পজিটিভ হবে।
Yes. What is u1? u1 is this, right? And u2 is the lower half semicircle. This is the upper half semicircle,
লোয়ার হাফ
upper semicircle, and this is the, yes, upper half semicircle, and this is the lower half semicircle, and x less than 0, so that means it is uh, the left half semicircle, and this is the right half semicircle. Okay, and using these coordinate neighborhoods, you need to define the associated coordinate maps. So coordinate maps are, so phi 1 from u1 to r, u1 to this will be your minus 1 1, yes, by phi 1 of xy goes to x. Okay, and in a similar way, phi 2 of xy will be x, phi 3 of xy will be y, phi 4 of xy will be y. Okay, so in a similar way, one can define the others. Okay, and then you will find out that these maps are continuous, and uh, actually they are homeomorphisms. Okay, so check that phi i's are homeomorphisms. Okay, so therefore this is again, so this says that this is an atlas of S1 consisting of 4 coordinate charts. Okay, and also one can define an atlas of S1 using polar coordinates, but that will be left as an exercise. Okay, using polar coordinates you can also produce an atlas of S1. Okay, and using this similar construction you can generalize these notions to any Sn. Okay, so the example number 4 will be any Sn. Sn means the n plus 1 r to the power n plus 1, so that mod of square is 1, k equal to 1 to n plus 1. Okay, so unit sphere, so n dimensional unit sphere Sn, and using the similar construction of coordinate charts and their associated maps that we have already discussed in S1 can be extended to this case Sn, and one may have the result that Sn will be a topological n manifold. Okay, just having the same kind of constructions. Okay, so check that Sn is a topological n manifold. Okay, okay, so I think let me stop here for today.